what I want to do now is solve the same system but using matrices. So if you use matrix notation to solve a system, you write, first of all, most of the time you use capital letters for matrices. So I like to use A lot. Most books use A for a matrix, and then you move on to B and C if you have multiple matrices. And we're going to call A the coefficient matrix. And all we're going to do is just write down the coefficients of our variables in the system. You know, when you're solving the system, the coefficients are really what you need to keep track of. You're trying to eliminate variables by making the coefficient 0. So we could just put them in a matrix and just deal with the coefficients, but just remember that, you know, we're dealing with a system. Okay? We have a vector b, and I like to use a vector symbol above b. In the book, you will see, and in a lot of books, you will see vectors in bold. And I can't bold my pen here, so without a lot of trouble. So I just use this vector symbol above the b to show this a vector. And the b vector is the constant on the right side of the equation. So we also have to keep track of this constant. You know, we don't just need to keep track of the coefficients, we need to keep track of these as well. And what you do is you augment these together. So augmenting, all that means is you just put them together in a single matrix. And I like to draw a line that separates where the augmenting happened, right? So this is kind of like where these two things are stitched together. So another useful thing is to label your columns based on the variables, right? So this first column, those are all the coefficients of x1. And the second column is all the coefficients of x2, you know, in your system. And the third column is all your coefficients of x3. And this guy, you know, again, it's just the b vector, so we'll just write b. And we're basically going to do the same process, but I'm going to take it a little further, and I'm going to write down some special notation to keep track of what we're doing. So I still want to make this 5 a 0. And remember what we did last time, we multiplied the first equation by -5 and we added it to the third equation. So now with matrices, we're going to call the equations rows. This is a row, this is row 1 of the augmented matrix, and this is row 3. And I'm going to write down the step that I'm going to do, and it just helps you keep track of your work, because some of these things can be kind of tedious and hairy, and you want to be able to go back if you make a mistake and kind of check and see what you did. So the row that I want to change is the third row. I don't really want to change the first row, I'm just going to use it. I want to make this 5 a 0, so I'm going to say I'm going to replace row 3, and I'm going to write down what I'm going to replace it with. So I'm going to replace it with row 3 minus 5 times row 1. Right, that's multiplying row 1 by -5 and adding to row 3. And you could write it that way as well. You could write -5 row 1 plus row 3. I just kind of like to write this in the other order. It doesn't really matter. As long as you know what it means, that's fine. And I'm going to perform the operation. And again, we're doing this to a matrix, but these are equations. Each row is an equation, so you can't do anything to the row that you can't do to a regular equation. So I'm going to write down all the rows that I'm not changing. This is kind of confusing to some students. Yes, I'm multiplying row 1 by -5, but I don't want to change row 1 because it's nice the way it is. It's got a 1 in this position. We want to keep that 1 there. So we're only going to use this row to change row 3. So now we're going to do the operation. We're going to multiply this by -5. And if you want to make notes, to kind of help you visualize this, if I multiply this by -5, that's going to be -5, 10, and -5. And I'm going to add it to the third row. -5 plus 5 is 0. 10 plus 0 is 10. -5 plus -5 is -10. And 0 plus 10 is 10. Now, I didn't write the 0 down here, but -5 times 0 is 0. So that's what we got before, except before I simplified this, right? I simplified this third row, this third equation. So how do we do that? I'm just going to say replace row 3 with 1/10 row 3. That's just going to divide that row by 10. So again, I'm going to write down all the rows that I'm not changing. And then I'm going to change the third row. It's going to divide all those by 10. So before, I switched these two equations. So in the matrix notation, when you switch two rows, you just say replace row 2 with row 3, and it works vice versa. So now I'm going to put the third row in the second place and the second row in the third place. And now I'm going to use this 1 to eliminate the 2. Now you might think, well, there's a -2 right here. Why don't we use that one? The reason is if I add this 1 to the third row, it's going to mess up this 0. I want to keep these two zeros because that means those are variables that have been eliminated, right? So I want to keep those variables eliminated. I don't want to add 1 here and it's going to mess up that 0. I want to eliminate this variable where the 2 is, and I also want to keep this 0 that's the x1 variable eliminated in the third row. So I'm going to use this row. I'm going to multiply. I'm going to change row 3 first of all, and I'm going to multiply row 2 by -2 and add it to row 3. So I'm going to say replace row 3 with row 3 minus 2 row 2. And again, if you want to write notes, so that would be -2, this would be +2, this would be -2. And of course this is still 0. And you can see this is a long process and we're going to make it longer, but you'll see how nice it works out in the end. So I'm not changing the first row. I'm not changing the second row, even though I said I'm going to multiply it by -2. I'm just using that row to change the third row. The only row that's going to get changed is the third. So -2 plus 2 is 0. 2 plus -8 is -6. -2 plus +8 is +6. And last time we did this thing, we said, let's simplify this equation. So I'm going to replace row 3 with negative 1/6 row 3. That's going to divide that by negative 6. For now, I'm going to write down all the steps just so we are on the same page. Okay, so it might get, if you're getting bored, just fast forward. Okay, if you know what's going on, go ahead. All right. So at this point, this is in triangular form, but we want to take it a step further. We're going to keep eliminating as much as we can. So I'm going to take the 1 that's in the middle. I'm going to use it to eliminate the negative 2 in the first equation. So that's going to be changing the first row with the first row plus 2 times row 2. So if I multiply this row by 2, that'll be 2, negative 2, 2, and I guess that one's 0. And I'm going to write down all the rows that I'm not changing. Again, I'm not changing row 2. I'm not changing row 3. So the one I'm changing is the first row. 1 plus 0 is still 1. I don't want to lose the 1 here. Negative 2 plus 2 is 0. And then 1 plus negative 2 is negative 1. And then I have 0 plus 2. That's going to give me 2. So, question again, why did we use, why was it okay to use this row? Well, first of all, this 0 is not going to change this 1. And I want to keep the first column as 1, 0, 0. Right? I want to have this 1 in the top, and I'm going to try to eliminate these 2, and I want to keep these eliminated. Right? So next, I'm actually going to do a 2 and 1. So there's sometimes you can do multiple steps if you want to. If you don't want to, that's fine. You can do them separately. But I want to eliminate the third variable from the first and second equations, first and second rows. And I'm going to use the third row to do that. It looks pretty simple here. The 1 is going to eliminate these negative 1s, and these zeros aren't going to mess anything else up here. And I'm going to explain why we want this particular form in a second. Okay, when we get done, I'll go through why we did it this way. So I'm going to change row 1 by adding row 3. I'm going to change row 2 by adding row 3. So the only one I'm not changing is row 3. So let's do the first row. I'm just adding row 1 and row 3. So 1 plus 0 is 1. 0 plus 0 is 0. Negative 1 plus 1 is 0. And then 2 plus negative 1 is 1. And then let's do the second row. 0 plus 0 is 0. 1 plus 0 is 1. And then negative 1 plus 1 is 0. And 1 plus negative 1 is 0. You see I've got this particular format here. I've got 1s in this diagonal, and I have zeros everywhere else. And look at the right side. So remember that these columns represent variables, right? These are the coefficients of x1, x2, and x3. And the rows represent equations, and this line that I draw for the augmented matrix it represents the equal sign. So if I rewrite these equations now, the first row says 1x1 plus 0x2 plus 0x3 equals 1. And the second row says 0x1 plus 1 times x2 plus 0 times x3 equals 0. And then the third row says 0x1 plus 0x2 plus 1x3 equals -1. Now that is the same solution that we got when we did back substitution. See that 1, 0, -1. With this matrix elimination method, we can keep going until we eliminate all the variables that are possible. Sometimes you can't eliminate all of them. But here I eliminated 2 from each equation, and what was left just gave me the solution, which is kind of neat. So again, we would write our solution as an ordered triple in this case. So that's a point in 3 dimensions, right? So the process that we went through is called Gauss-Jordan elimination. And sometimes it's just called Gaussian elimination. And this is, of course, a famous mathematician and physicist, Carl Friedrich Gauss, kind of worked through how to do this. And Jordan was a later mathematician who kind of made this popular. He kind of started using it a lot and got other people to use it, I guess. So some people just drop Jordan from the name. And it's not Jordan. I know that's how most of us pronounce it, but he pronounced it Jordan. Okay, so I'm kind of careful on how I say that guy's name. So Gaussian elimination or Gauss-Jordan elimination, the process is to get a 1. Let me do this in green. You want to get a 1 in the top left corner first. And we already had that, so we didn't talk about that much. And then you're going to eliminate the other variables in the same column. So you're going to go column to column. So I've got this 1 in the top left corner. I need to make the ones below it, or the entries below it, 0. And once we get that at this 1, 0, 0 in the first column, we move to the second row, and we want to make the entry in the middle a 1. And I did that by just switching these 2 rows. Right, so I got my 1 there. And then you want to eliminate the other two coefficients in the same column. So I took a few steps to do that, but I ended up getting this 0, 1, 0. The third step, when you move to the third column, you're going to make this entry a 1, and in this case it already was 1, and then you eliminate the other members of that same column. So we get this. And if you can get it in this form, you get a nice solution, and the solution actually ends up being this third column, right? For this type of system, right? We're going to look at a lot of different examples where things don't work out this way, okay? But when you have a single point solution, it's going to kind of be in this form, right? You can always simplify it to that form. If you get other types of solutions like infinitely many or no solution, you're going to encounter different things, okay? And if you have different number of variables as equations, you can get different looking systems when you reduce them. But if you've got the same number of variables as you do equations, 3 variables, 3 equations, or 2 variables, 2 equations, or 4 variables, 4 equations, and you're going to get one single solution, you're going to be able to reduce it this way. Okay. Now this method takes a lot of practice, and we're going to do a lot of examples, but this requires some getting used to. Okay. Now the original equations are in 3 variables, right? That means we could graph these in 3 dimensions, and in fact all these equations represent planes. Instead of lines, we have planes. Flat planes in, flat 2-dimensional planes in 3-dimensional space. And if they all converge at a single point, what you get is a system, or a graph like this, where each equation of the system is these planes, and you see they're intersecting at a single point here. This is the actual graph of the system that we solved, and we get 1, 0, -1 there.